Alright, silly people, here's the situation. We're doing a transformation matrix, specifically the rotation matrix. And we're going to try and prove that under a rotation that the value of a dot product remains the same um, when both vectors become rotated. So I wrote down what the form of a rotation matrix is. The new matrix A bar is equal to the cosine phi sine phi minus sine phi cosine phi matrix times the column vector A. Um, doing a little bit of matrix multiplication, you can put it in this form where it's AY cosine phi plus AZ sine phi minus AY sine phi plus AZ cosine phi, which is cool. We can go ahead and introduce the vector B, also indexed y and z, and also being rotated by the same angle, phi, right? And then, so it's by, bz, and it'll take the same form on the other side, so it's going to be by cosine phi plus bz sine phi minus ay, whoops, minus by sine phi plus bz cosine phi. And so the dot product between the two new rotated vectors will be ay bar by bar plus az bar bz bar. So using our definitions of the rotation, it'll look like this: ay cosine phi az sine phi times by cosine phi, whoops, by cosine phi plus bz sine phi plus minus ay sine phi plus az cosine phi times minus by sine phi plus bz cosine phi. And then doing a little bit of foiling, you see that it's just ay by cosine squared phi plus ay bz sine phi cosine phi plus az by sine phi cosine phi plus az bz sine squared phi. And then that's going to be ay by sine squared phi plus, or minus actually, minus ay bz sine phi cosine phi minus az by sine phi cosine phi plus az bz cosine squared phi. Super. Already you can see that these terms cancel out. You have a plus and a minus on both of these guys, so just get rid of those. And then what you're left with is ay by. One of them was multiplied by cosine squared phi, the other was multiplied by sine squared phi. And then you had az bz. One of them was cosine squared phi, the other was sine squared phi. Cosine squared phi plus sine squared phi are equal to 1, so these are just ay by plus AZBZ. So what we just did there is we proved that the dot product, the value of it is conserved under rotation. Epic. The next part of the problem says, what constraints must the element of the three-dimensional rotation matrix satisfy in order to preserve the length of A for all vectors A? So if you rotate a vector A, summing over I, so that you catch all of the elements, then the way that you're doing it is you're summing over I and j the tensor Rij Aj, right? You have a vector A, then when you rotate it, you're just multiplying it by the rotation matrix. And so to maintain the magnitude of the vector, this has to be true. So we're doing the magnitude of the new vector has to be the same as the magnitude of the original vector. And so plugging in the definition of the rotation, you have the magnitude of the sum over I and j, Rij Aj, better be equal to the sum over I of Ai. Right. Cool thing about this notation is that you can pull the sums out of the magnitudes. Whoops. That way stuff doesn't get confusing. And then you can split up the magnitude of Rij Aj into the determinant of Rij and the magnitude of Aj. Right? Second cool thing is that the sum over j of Aj is the exact same thing as the sum over I of Ai, which means this term cancels out this term. So really what you're left with is the sum over, really what you're left with is the sum over I and a j, the determinant of Rij is equal to 1, and then you can get rid of that summation and say like this. So what is that saying is that the determinant of the rotation matrix has to be equal to 1 in order for the length of the vector to be the same for any vector A. I think there are multiple solutions for the rotation matrix that comply to this constraint, and so I'm going to leave it there. But of course, there's a general form for the rotation matrix that I'm sure will come up later. All right.